Hi, Navin. We'll wait for some more time for others to join.
Okay, no problem.
என்னங்க அப்படின்னா அப்புறம் பார்க்கவே இல்லை சார். நான் ஃபர்ஸ்ட்ல குறைச்சிக்கணும்னு நினைச்சிட்டு நல்லா பாருங்க செகண்ட்ல தான் அது எதுக்குமே ஆகாதுங்க.
We'll just wait for 2 more minutes and we'll start our class. We'll start the class at 6:05. Meanwhile, if anyone has any doubts from previous class or the present class, you can ask.
Hello, good evening, Rashi.
Good evening.
Yeah, Arjun here, and just wanted to, the last class we had asked about the reference textbook by Professor Ramesh.
Yes, Arjun, I actually texted sir as well as the students under them. There is no PDF as such. It seems like there is a transcript that is available along with the courses, like how it is given, the subtitles and all, right? So
Yes.
that is it. It seems. Yeah, you mailed me. I asked then and there only. I thought of informing you, informing to everyone else in the class. That's why I kept.
No problem. Then subsequently in Professor, I think third or no, fourth or fifth lecture, he mentions about the reference textbooks we can refer, right?
In the second week, right?
Yeah, in the second week class. I'm not sure whether fourth or fifth. But and so the first textbook which sir mentioned was I think from Elements of Fracture Mechanics by Prashant Kumar. And the same thing I checked in Amazon and Flipkart. Both are actually out of stock.
Oh yes, I was telling to keep it one with us, like it'll be easy for us, no?
Yeah. So I mean, because sir had in the, I think in the list which he had given, we took that the first book which he has listed was by Prashant Kumar. So we took, okay, that may be the most useful one for us. But,
yes, yes.
yeah, the same is actually showing out of stock. So yeah, so as of now, I'm relying on sir's video lectures only because I take down notes.
Yeah, sir. To be frank, sir's video lectures are also good, but yeah, it will be nice if we have one book like along with that. So you all registered for exams, right?
Yes, I have it.
I got it. Okay, so I'll if you try to get it in your institute if it is available.
Okay.
Is it?
We are
You can check in your library.
Yeah. So what I'll do is, normally when we find that there is no, I mean, Amazon and Flipkart doesn't have, we will search for some PDF free download, no? So
Yeah.
yeah. So there is Prashant Kumar's. Prashant Kumar's book, that Elements of Engineering Fracture Mechanics. It is available as a PDF online. I think, yeah, as a part of a scanned copy. So I have downloaded and kept. Let's see, not referred yet.
Let's see. I'm not using any textbooks for until right now. Like before, when I was doing my BTech, that time we used to use fracture mechanics. Especially we used to use Detour only for that fracture mechanics. And but then what sir is teaching is kind of even more detailed compared to what it was given. So should I ask to sir like if they can provide PDF or something? Will it be useful?
Yes, ma'am. Actually, what is surprising is that in the NPTEL in the course front page, no, there is a textbook link is there. I mean, there's a textbook button is there.
And
But
it's not working.
no, it is working. But except for English, all other languages it is available. Like I think Hindi, Tamil,
Yes, great.
Malayalam. Yeah, but the English one I couldn't find. I don't know if others have found an English copy, but Sir's textbook in other languages are available in that NPTEL front page itself, for the course front page under textbooks column.
Did anyone find in English? Did anyone else?
For
Okay,
English, it is not available. We couldn't download actually.
the reference is kind of becoming very crucial, right? Like we are not able to find the book either in offline or we are not able to find online also. So I'll talk once today with sir. I'll text him if whenever he's free, he'll reply to us. If he has some PDF form or something, I'll ask him to share it with us. I asked last time only, like for especially only for the book, sir was telling that in his book. So PDF it was not available, it seems. That's what I got the news from their students. PDF was not available. Only the transcript of that will be available in the NPTEL only. So we'll get started in. Yeah, I'll just wait for a minute, one more minute, and we will start. Arjun, is it fine, like regarding the textbook?
Yeah, so I think is the screen visible?
Yeah, it is visible.
Yeah, so in that books, this is what I was talking. In the books, if you click books, all the four languages are available. English is not. So maybe, if NPTEL can upload an English version of Sir's book, it may be useful for us.
Okay, this is the book that you were telling. Like this is sir's book only, right?
Yeah, this is all Sir's book. None other in all four Indian regional
Okay,
languages.
okay. Anyone else is using any other reference? Yeah, we will start the lecture now. Good evening, all. This is Rashi again. I'm studying in IIT Delhi, doing PhD under Professor Jayan Jain sir. This is Engineering Fracture Mechanics Interaction course taken by Professor K. Ramesh, Chair Professor at Department of Applied Mechanics in IIT Madras. So last time we stopped at Moore Circle. First, I have to apologize for one thing. Like I have made like last time Arjun was telling that to discuss this point. First, I want to share the mistakes that I have done. In this question, I said that C is the answer, but then here it is marked as lesser than or equal to. Actually, it should be greater than or equal to. Everyone are able to see my screen properly? Huh?
Yes, madam, we can see. We're able to see.
Switch off this one. Okay. Yeah. So this is one mistake that was there in previous like interaction session, and we also said that previously I that I'll talk to sir regarding this, and the answer was actually theory of failures, not the tension test. The answer was not tension test. The right answer was theory of failures. I said that I'll talk to sir. Like, yeah, one person, I think so, Arjun or someone, I don't remember exactly who was pointing out that Suresh, right?
Yes.
Suresh was telling that it was theory of failures. Yeah, you were right, actually. And even I got confused there a bit. Like, we will get the yield stress using tension test, and using that we can actually when combined stresses are acting on the material, we can find out when it will start fracturing or like yielding, the maximum stresses will be applied or anything using a theory of failure. Yeah, you even pointed out one point last time, I remember. What if we, two different type of stresses are acting, bending or torsion at the same time, then the yield will be happening sooner. So that point was very valid. Like, and I even had a talk with Ramesh. So yeah, that answer is theory of failures, not the tension test. And then we'll be studying these things detail later on in sir's class also. So I want to say sorry for these two things. And yeah, we will start with Moore circle.
Sorry, ma'am. Actually, just want to add something here. There is no need to be sorry. It's a discussion, and we are in the process of learning. So
Yeah,
it's okay.
but still, like I was telling to everyone, even I was trying to convince you also that tension test was the right answer. So that's the reason only. I'm sorry, else like even I should have done a little bit more study on that comparatively. So that's why. And so like now everything is clear. And I made the mistake I made last time was discussing the problems which was already on live. So from this week onwards, actually we'll not be doing that. We'll be taking the sir has given some other problems to solve it. Some like so we'll be doing the similar way we have done previously. We'll be trying to discuss the topics under that, like under one question, how we discussed many topics under that. Like we'll try to do that thing again, same. But then we'll not be discussing the assignment which will be live. Once the assignment is submitted, we can discuss again in the next class if you guys have any doubts or something. Fine. I hope that's fine with everyone. I know it is not fine with
Really
everyone.
tough. Yes,
Huh?
they are. Since are, we are finding it tough actually.
We are finding it tough. We'll try to like see what we can do. It at the end of the day, marks doesn't matter. How much we gain the knowledge is what matters. So like and I don't think so these assignments are also graded. So it is kind of like to let you think. Again, if it's required, we can discuss the problems. It's not a problem. Like we can have again the discussion of that in in the beginning 1 hour. We can do the discussion of previous assignment which you already solved and submitted. And next 1 hour we can do the discussion of that lectures. Will that be fine?
Okay.
I hope it's really fine. Yeah, because that's what I've been told and I shouldn't discuss exams. So yeah, coming to Moore's circle, even in the Moore's circle, the calculation error was there. And anyway, we will try to do the Moore's circle. I said I'll be discussing more about Moore's circle. And these are stress elements, like considering that we are having some amount of stress we are applying in X direction and Y direction. And from this notation, we can say that as it was we are applying pulling up, it is in tension. And if it was in compression, the sign notation would have been in this direction. So, and we will just first go with the Moore circle. Now, before even going with Moore circle, I want to say you how like why Moore circle is kind of very easy and very important compared to like we calculating using equations or formulas or like any other thing. So these are the notations first we'll be talking, like when the stresses are in tension, we consider them as positive. As stresses are positive in both the direction X and Y. Now it means that it is in tension, it means it is in positive. And if the stresses are in compression, it means the stress sign we can keep it as a negative. And for shear stress, if it is happening in a clockwise direction, anti-clockwise, counterclockwise direction, then we'll consider it as positive. And then if it is happening in anti-clockwise, clockwise direction, this will be positive and this will be negative. So before that, we'll just try to understand. We'll put like some numbers for xy and xy and xx, sigma x and sigma y. Like just consider we are applying 20 MPa in x direction and 7,
Madam,
and then we are
tensile and compression. Tension and compression.
tension will be
That notation. Can you please tell us that positive?
yes,
negative?
tension will be in positive.
Okay.
Is positive and compression will be negative. Okay.
Okay.
If it is in counterclockwise, this is for normal loads. This is for shear load, shear stress. Shear stress. Okay. So now consider we are applying some amount of load in X direction, Y direction, and some amount of stresses is happening. And we know that principal stresses will be acting upon it, but we don't know at what degree it will be acting also. And at what angle, what plane, all those things we really don't know. So we'll be trying to calculate. Before that, we will try to rotate the whole sample in one direction. Either it can be in counterclockwise direction or in clockwise direction. We will rotate it to 180 degrees Celsius. So the this axis, this sigma x will go to this side. Until then, we'll try to find out how the stresses are varying, and how the stresses are. We'll see how the stresses are going to vary. Then we will be able to see that stress is going to increase and then attain some maximum and then decreases and then attains minimum. The difference between these two will be 90 degrees. And if you try to plot the stresses versus the angle up to 180 degrees, we consider that we have done rotation up to 180 degree. And then we will see that in this 180 degree, we'll be having maximum stress as well as the minimum stress. When you see this is for normal stresses, and when you plot a similar way for the shear stress as well, you can find out that at maximum and minimum, the shear stresses will be 0. So you get the point, like, and the difference between maximum and minimum will be 90 degrees. So when the shear stresses become zero, where that corresponding normal stress will be called, whatever we call it, is principal stresses. As you can see, even in the maximum, the shear stress is zero, and then even in the minimum, the shear stresses are zero. This is a shear stress curve. And then the corresponding maximum and minimum are called principal stresses. So the corresponding maximum, minimum normal loads are called principal stresses. And at what angle it happens, that we can calculate using we have formulas, but that becomes very difficult. That's why the Mohr circle has been formulated, so that it becomes very easy to find out whatever the stresses in whichever angle we rotate, what will be the stresses present in that particular angle. So Mohr circle is just to say it's an easy determination of a normal and shear stresses without using any shear transformation equations. Like we have shear transformation equations, like as you know, either it can be sigma max or sigma minimum. It will be equal to how much we are applying stresses in x direction as well as y direction. It depends upon both of that. So the formula will be given as, like, I'll write out the formula, whether it can be sigma 1 or sigma 2. That depends upon sigma x, how much we are applying in x direction, y direction divided by 2, and plus or minus root of this. Plus or minus will be based on whether maximum principal stress you are considering or minimum principal stress you are considering. Divide in the root of sigma x minus sigma y the whole square by 2, plus how much the shear stress is happening in xy direction the whole square. This will be the formula, but for it doesn't become easy for using formula every time. Using formula will not be that easy when the complicated situation or the loading will be happening. Here it is just tension and compression. If the loadings are in very complicated, whether both bending and tensile loadings are happening at the same plane, so how much is the principal stresses to find out, it will become difficult. So in order to simplify our life, Mohr circle has been like we use usually Mohr circles. So Mohr circle, how it is done, it is a normal 4-quadrant. We will be plotting shear stress versus normal stresses, normal stresses. So in this, when we are applying in tension, as I told previously, tension loads will be in positive side and the compression will be normal loads. If you apply in tension, it will be coming in positive x-axis. If it is in compression, it will be going in negative x-axis. And in the similar way, if the shear is happening, as you can see here, in this xy plane, you can see that shear is happening in counterclockwise direction. So here the shear stresses will be positive. So if you see in Y plane, the shear stress is happening in clockwise direction. It will start moving in this direction. So shear stress will be negative in YY plane, and shear stress will be positive in XX plane. In this plane, if you consider, shear stress will be positive. In this plane, shear stress will be negative. So coming to this point, so shear stress will be negative here actually. Negative shear stress will be, you'll be getting negative shear stress. I'm sorry. If we have
And
any
one small
negative shear stress,
clarification.
yes.
Inside the square root is in the formula sigma x by sigma by 2 the whole square, or I think the formula will be sigma x by sigma by 2 the whole square.
This one?
Minus only, ma'am, but the whole square will be divided by 2, the whole square.
Actually, the whole.
Yes, ma'am. Minus
Yeah,
will be the
this
same.
yeah. Okay, yeah, we have to divide by 2 and then whole square. Yeah, if it is if compression is happening in x direction, like the question we have 100, and then the tension in y direction 10 MPa, then we have to 90 by 2 it will be, yeah, correct. So shear stress will be negative in upper quadrant, and shear stress will be positive in this quadrant. And then normal loads, as I said, if it is tension, it will be in this quadrant. And if it is compression, it will be in this quadrant, in this axis. So how we'll be plotting more circle is, first we have to take a, as we know that here, as we saw previously, one second. As we saw previously, in x sigma x was having positive shear stress. So your point will be in this somewhere here. Some, like, it depends upon what how much you are applying a load in x direction, and sigma y again was positive because it was both in tension. But then shear stress was happening in negative direction. So we'll be pointing one more. Sigma y minus of, and then when we'll be joining this. So consider the circle is nice and circular, okay? And then if we rotate a sample in different direction, then we'll be getting how much stresses are acting in each plane, like in that XY direction. So in this way, even if it is in bending, or both bending and compression are acting on the same sample, I mean on or different modes of stresses are acting on a material on one particular plane, then we'll be able to still get the how much amount of stresses are acting with different angle. And whatever
Madam?
we yes.
Can you please repeat this as construction?
Yes. So first we'll be taking, first step is to plot, take the sigma x, and then stresses, so how much stress is happening in xx plane, sigma xy plane. And then you have to see whether it will come in positive or negative, depends upon the, you have to see whether it is stresses are acting in xx direction, in counterclockwise direction or clockwise direction. So depending on that, you have to take the point sigma x, comma shear stress xy, like how that these values you'll be getting this how much you are applying in tension or compression, or how much shear stress you are applying, you will be knowing. And then from that you have to find out points. You have to first take sigma x and sigma xy, and then you have to point another sigma y, and then minus of sigma xy. Here it is minus because we have if shear stress is acting positive in positive direction in xx plane, then it will be acting in negative direction in yy plane. So that's how it will be in equilibrium. So if shear stress is acting in negative direction in xx plane, then it will be the opposite in yy plane. So we have to take this point and then join through the join through the axis, and this whatever the join through the axis, and then make a circle around it. And whatever the circle you get, the radius of that will be the maximum shear stress maximum. the radius of that will be the shear stress maximum, and that will be corresponding to this one in your formula R. This will be the radius in when you compare with the formula. And then whether sigma, this is, we already saw that principal normal stresses will be maximum or minimum when it becomes shear stress should be 0. So we have two values where the shear stress is 0, this one value 1 and 2. So as we know that principal stresses sigma 1 is higher compared to sigma 2. So this is sigma 1 and this is sigma 2. As we always say that sigma 1 will be greater than sigma 2 will be greater than sigma 3. Like that's how we take the principal stresses. That's how to simplify our life. So that's all. So this will be the sigma 1. This is sigma 1 because here you can see that shear stress is 0 on this plane. As you know that shear stress is 0 on this plane, and previously also we studied that principal stresses will be acting when a shear stress in any particular plane only when the shear stress is 0. So sigma 1 and sigma 2 we will get it like that, and whether it is sigma 1 or sigma 2 depends upon which is the highest, and you assign that highest value to sigma 1 and the lowest one to sigma 2. Did you get it until now?
Yes,
I hope
madam.
you.
Yeah.
Yeah. So previously we saw that the sigma 1, the principal stresses were separated by 90 degrees. But here we can see that it is approximately around, it's not approximately, it is around 180 degrees. So it is 2 times whatever we have applied. So here, whatever, how much here we have to rotate to get the principal stresses, that is given as 2p. That's why 2 theta p. This is at what angle the stresses will be maximum when you rotate that plane. So that you will get it using from this only. How much ever angle you get here, you have to divide it by 2. That's that much amount of degree of rotation is required for you to get principal stresses in that particular plane, and principal maximum and minimum principal stresses. So until now it's clear.
Yes. Yes.
Here we can see previously I said that between maximum and minimum, the difference is 90 degrees. But here you can see that it is 180 degrees. So that's why it is twice of that whatever we got previously. That's why it is we have this 2 number. That's all. So sigma 1 will be sigma x by 2 plus r, and sigma 2 will be sigma x plus sigma y by 2 by plus minus r, sorry, minus r. And r is maximum shear stress. Fine. So I'll give you guys 5 minutes. Since I don't know, it's required 5 minutes or 2 minutes, or else we will try to solve the problem that is given. The problem we have given is we are having in compression 100 MPa. And then this is also in compression 10 MPa. This is shear stress is happening in MPa. Can anyone tell me the first the coordinates first it as it is in compression, which side of the which side we will be drawing the circle?
The
I really
negative
want you
coordinate.
guys answer in the negative. This is a compression, right? So we'll be
Yes.
drawing it in the negative coordinates. Yes. So and then the points will be
The points will be minus 10, comma 80,
minus 10, comma 80. Good.
and then minus 100, comma minus 80.
Minus 100, comma
Minus 80.
minus 80. Yeah. It should be minus 80. Yeah. It will be in y direction. Yes. So if we try to plot it, and then we can even find out the question, the 16th question, the questions they asked using more circle as well as using the equation. And I'll give you 2 minutes. Let me see who will get the answers right. I want sigma 1, sigma 2, and as well as the R.
Madam,
It's
how these points
6:36.
have come? Can you just
Yes,
10
I'll
and
tell
80?
you. Minus is because it is in compression in XX direction. Can you see it? It is in compression. We are applying compressive load.
Yes, yes.
So it is in -10. And then as you can see that the shear is happening in this direction. So if in this direction, it will be counterclockwise. So it is positive. And the positive will lie in this quadrant.
Okay.
Right? And similarly in the y direction also, 100 MPa is applied in compressive load. So compressive stresses are applied. And as you can see here, if in y direction, it will be in clockwise direction. So that's why it is negative. Got it?
Yes, madam, got it.
Yeah, who solved?
I think sigma 1 will be 36.787.
Like 36. You have to tell me the name also. Who solved this?
Naveen,
Naveen. Okay, nice, Naveen. Sigma 1 is
36.787.
36 point. Can you round it off to 2 digits?
36.79.
Correct. MPa. Yeah.
Sigma 2 is minus 146.79.
Yeah, I want to. Who is telling this?
Arjun.
Minus 146 points.
7.
And then 2 max is
91.
someone else also can tell, huh?
Minus 91.787.
91.787. So 779. Perfect. So previously also there was some calculation error I made, so I gave the answers wrong actually. That's one thing. That's why I haven't. Huh?
Quickly, can you solve here?
Yeah, we can solve, but then okay, fine, we can solve. Like sigma 1, sigma x is how much? Sigma x is
-10.
And sigma y is?
Sigma y is 80.
How is 80?
Sigma y is minus 100.
Okay, okay. Minus 100. Sorry. Tau is 80 and minus 80. Okay.
By 2. So this will be plus, and then root of sigma x will be -10 plus 100 divided by 2 the whole square plus 2 is 80, right? 80 square. So if you solve this, who asked this question? Who wanted to solve me this? So just tell me how much you're getting the value.
Yeah, madam, I have to calculate that.
Calculate and tell.
Madam, please continue. It may take some time. I cannot calculation. No, actually, the procedure only just I was asking for that formalistic.
Yeah. In sigma 1, it will be plus, and you have to just calculate R first, when the radius of the circle, or you can say tau max, that is maximum shear stress, and then calculate sigma 1 and sigma 2 by adding and subtracting. That's all. It's not that difficult, but it's kind of very
Yeah, it's
important.
clear.
That is why,
It's clear. Now I got it. It's okay. We can go to
I keep doing this. So this whole thing, the 2 by whole square is 80 whole square. Fine. So we can also calculate using Mohr circle. We can also do using the equations that we have. We can also cross verify whatever the results we get from Mohr circle to this one. Mohr circle becomes more useful when we are doing further, like complex loadings, like or by two different loadings are acting on the same time. That time it becomes more easy. So this is just simpler way for us. Even in 3D also we can do that. This whatever the Mohr circle I discussed is just in 2D. Not we are not considering any. We are thinking that principal stresses. We are not applying any load on in Z direction. So we don't have much thickness of the material. That is what we are considering here. And someone asked me for discussing some case study for stress corrosion cracking, right? I don't remember who was that. Is it required to do the discussion, or like we will go further? Who asked me? I did it. I don't remember me. Is that person here today who asked me to discuss case study on stress corrosion cracking? So if we have time at the end, we will discuss then. So this is actual study that happened in MRPL. Even I did it during my BTech, and this was my BTech project also. So we will be seeing where are the stress concentration region, and in real life also the cracks happened near that. As you can see, these were the stress concentrated region, and the crack happened near those regions only. And how is as you can see, the component is made up of mild steel, and why we are worrying so much about this one was like if it is required, if you guys are interested, we can discuss now, or else we'll go further. What do you want me to do? You want me to continue, or we'll go further and then we'll come back to this at the end?
I mean, if you have time,
Please
we
go
can
ahead, madam.
come back
Please
and
go ahead, madam.
this is second
We will go
week
ahead.
syllabus is also there, no? Second week also we have to discuss quickly.
Yeah, we have to discuss. Yeah, we will proceed to further questions, and we'll try if time is available, we will discuss at the end. Okay. So the question, as I'm hoping that everyone has seen the second week lecture, and it's kind of a interaction session only. I'll not be giving the answers. I'll try not to give the answers. I want you guys to give the answers to me. So these assignment questions are from previous year when it run. So chances are there, like the topic which are coming under this also, it can come in your exams. So try to pay a little bit attention and like try to analyze the answers and then give the reason. So we will discuss a present assignment if possible in the next week. Okay. So the local plastic deformation is beneficial from point of fracture mechanics because plastic zone can prevent the crack from growing. Is it true or false?
And sometimes it is true.
Sometimes when is it?
For a brittle material, if we apply sudden load, after the release of load, the plastic deformation will help in closure of the crack.
Correct. Sir has showed one video. So you're telling that like if plastic deformation happens, it's permanent deformation. So it will not come back to its original place, and then the crack length will be higher.
Not higher, but in case of brittle material, if you remove the load, the crack have the chances to close itself.
Okay, so tell me in this way, in brittle material, do you think the plastic deformation is going to happen?
Deformation, there won't be any indication like that. There will be sudden failure.
Yes. So plastic deformation is usually seen in which material then, brittle or ductile?
Ductile.
So like which one do we prefer, like ductile material or brittle material?
Whether what type of application we are considering.
What type of application?
Depends on application we can use the material.
Brittle or ductile.
Hmm.
So, do you want local plastic deformation to happen in your material during the crack if crack is present or not? The point is that you don't want.
No.
So, what are the other answers I have?
That is an indicator it's going to fail.
It is true.
Who is this?
Suresh.
Suresh. Okay, Suresh is telling true. And who was talking before?
No, actually, the tip of the crack, if it is plastic, it blends actually because it will prevent the further growing.
Exactly. That's the point. If there is a plastic deformation happening, if the crack tip radius is very sharp, because of plastic deformation, the chances of it getting blunt will be very high. If the crack gets blunt, then the severity or the stress concentration at the crack tip will be not very high. So as the radius increases, the critical stress at the crack tip will be lowered. So it will not be like it can be way less than the failure stresses that required. So plastic deformation is actually beneficial from the point of fracture mechanics because plastic zone can actually prevent cracks from further growing. It's not only that if it is a brittle material, the breaking of the bonds will be very easy, and then like further breaking becomes more easier because there will be in ductile material when plastic zone happens around that and around the crack tip, the plastic zone will be happening. So the propagation of the crack will be slower. That's why local plastic deformation is required, and it is true actually. This was from previous year, and we have another question. Fracture toughness and the toughness of the material are same. They can be used to characterize characterize a crack. Is it true or wrong?
Fracture toughness and toughness are very different.
How is it different?
Toughness is generally the area that we have seen in the stress and strain diagram, the area below there. But when it comes to fracture toughness, it is generally dealing with the mode of failure. It is in mode 1, mode 2, mode 3.
That okay, I understand that fracture toughness is different for different type of modes, but it can even happen at the combined mode also, right?
Okay,
so like I just want is it true the fracture toughness and the toughness of the material is same?
They are not same.
They're not same, yeah. And the toughness of the material is the ability of the material, like consider that there are no flaws or anything in the material, and even if the flaws are there, but when you do the tensile testing, after we get the curve, how much is the area under the curve? How much is the energy? How much a material can store energy before the fracture can happen? That is the toughness of the material. That contains both resilience as well as the ductility of the material. That is resilience in the elastic zone and then resilience in the plastic zone. But the fracture toughness is like how much a material will be able to, if any crack is present, how much it is able to resist that crack propagation. Like how much it is able to absorb the energy. If it is a brittle material, it can absorb more energy and then it can absorb more energy and it can resist the crack growth, further crack growth. So it's the ability of the material, if any pre-cracks are present, to resist the further growth of the crack. How much it can absorb the energy. That's the difference. I hope you got the difference between fracture toughness and then toughness of the material. So fracture toughness can be used to characterize the crack, but then toughness we cannot use to characterize the crack. It's the material property, not if the cracks are present. We cannot say how the cracks are going to propagate or all those things we cannot say using toughness of the material. So it's false. So question 3, necking will always happen in the middle of the specimen when loaded in tension. That is assertion. And the reason behind that is necking happen at a location where the internal flaws in the material are mostly concentrated. So the option for you guys are both the statement are true and the statement 2 is a reason for statement 1. And option B is like both the statements are true. Statement 2 is not the reason for statement 1. Statement 1 is true, but statement 2 is not. Statement 1 is not true. Statement 2 is true. And these both the statements are false. So what do you guys think it's a reason?
C
is the answer.
C is answer. Who answered this?
Suresh.
Why only Suresh is there in the class? Okay, C is the answer. But before that, I want to discuss few things with you guys. So as we have seen, this is how the stress strain diagram will be looking like, right? So initially we'll be having a linear region where stress will be proportional to strain, and then comes a non-linear region. This I have taken usually for ductile material. And as you can see that with increasing the load, the stress increases and it becomes it goes to a point where it attains maximum strength of the material or ultimate tensile strength, and then it reduces from that point. Can anyone tell me why is the reason after attaining maximum shear stress or ultimate tensile strength, the material, the stress of the material reduces? There is a answer here only in the figure. Okay, can someone tell me why the shape of the tensile sample is like this?
The edges are required for gripping purpose. That's why.
Yeah, why you cannot grip like this?
Actually, just we want to see the necking and breaking at the middle portion. It should not be at the grips.
Is it like you wanna see only necking and breaking part? Nothing else is a reason?
Maybe the measurement of strain or something.
Measurement of strain what?
ABCD, like what is the dimensions are fixed, right? So when it is undergoing plastic deformation, that naturally that length will also increase.
Someone else is in the meeting. Can you come again? I'm sorry. So
ABCD in the
yes, ABCD.
You're concerned about what is happening in the region, with the boundary of.
So why can't we have something like this, completely straight? I mean, not like this, straight. Why can't we have like this? Okay, fine. You want this much ABCD thickness only, then have this much only. Why are you having extra, higher area here? Have this much only then, if you want ABCD only.
Can I?
Yeah.
The area is less at this gauge length, so that the fracture will happen at the reduced area.
So it's almost right. So we actually do it. Even we keep it this one as a circular. There because stress doesn't get concentrated. Like if we all know that if we keep the something like this, then stress concentration region will be there. That's why. So first thing is we keep it this for gripping purpose. That's fine, but we reduce the area at the center because we want the stresses to be concentrated in this region and the elongation to happen in this region. So as you know, the cross-sectional area in this region will be lesser compared to that of here. So the most stresses will be acting in this region, and then whatever the stresses we apply in tension will be concentrated in ABCD region, as you guys said. And as we know that when the width it is reducing, we cannot have a sharp sharp, what is this called? Sharp change. So we will be having some circular there. rather some circular, so that stress concentration region will not be there. And then whatever the properties that we get is because of this one. And then if any flaws and all are present, that is not our thing. We are considering that it is completely flawless material, and then we will be doing the tension. So that is what we expect, but that is not in reality. And then what happens, what I'm telling, this is one part. The shape of the tensile sample will be y in this. So this is one part. Now you got the reason why we have tensile sample in dog bone shape, so that the stresses gets concentrated in this region. And then when you grip also, some amount of stresses will be present in this region, because gripping also takes some stresses will be happening in that region. So, sir has already discussed one point. Like gripping also, it's like holding the material. So we don't want, so if you do the tension test having a same size throughout the sample, then the gripping will be here. The grippings will be here. So the chances of sample breaking because of the grip as well as the applied load will be higher in this region, in these two regions, compared to anything else. So how much the load we are applying in this region will not be able to calibrate. So in order to avoid that, we make it in a dog bone shape, so that the stresses will be concentrated in this region, and not because of grips or anything else. The fracture will happen only solely only because of applied load. Fine, you got this point until now. And the next point is up to the anti-belt tensile strength, the deformation will be happening uniform throughout the sample. When necking starts happening, whether it can be in this region or in this region or anywhere, when necking starts happening, then the area gets reduced in any particular region, and then so the stresses will be deformation will be happening more in that particular region compared to other region. So further, like that's the reason why the stress of the material reduces, because it will be concentrated in this particular neck region now compared to throughout the sample. Got it? And then keeps on reducing until the fracture happens. Is this point clear for everyone?
One question, ma'am.
Yes. I will be disappointed if you guys don't have a question.
Ma'am, you were discussing about the stress concentrations, but
yes,
the fracture of tensile specimen is happening because of this concentration or because of the voids, microstructural voids present.
Here I'm telling, here it will happen because of voids. Yeah, that we'll be discussing further. That is a next step, how the necking will happen. That I'll tell further in detail. But then why the shape of the sample is like that, and then why the stresses reduces after ultimate tensile strength and when the necking starts happening. This point you guys understood?
Yes, ma'am.
So I'll discuss that when the voids, that one I'll discuss again. So until now you guys understood, right? Until this point. That's all I want to know. I hope it is not too much. So yeah, we will go to next. So when necking will start happening, usually it will happen because if some it doesn't really matter whether it will happen in this region or in this region. Any region can it happen. It can happen. It will start by forming small necking region will be happening, and then because of further applying load, very small voids gets formed inside the material. Small voids gets formed. It can be in any random way, depending upon so it kind of voids will be present everywhere. It's not like it will be present only in particular place. So where the internal defects will be more, that's where it starts reacting. That's where it starts forming more neck region. And then for now we will consider it is happening in the center of the sample. And then when we further apply load, a bond gets broken because of these imperfections or defects or vacancies or anything it can be. It starts breaking locally. So it doesn't have to be in a straight manner. it starts breaking in a locally, and but then as you can as you can see, the voids are present more in this region, so it starts forming coalescence of the these cavities or voids, you can call, starts happening and forms a very big void compared to smaller void. If the crack is very small, if the void is small, nothing will happen. But when it gets coalescent, when it gets combined and form a bigger crack, that's when the failure of the sample happens. So further, it has further it gets once it reaches a you know typical crack length, it gets failed by pure shear. Pure shear for sample will be at maximum shear will be happening at 45 degree. For any tensile sample, when it is applied in a 90 degrees, the pure shear will be happening at 45 degrees. That will be maximum shear stress will be applied at that angle. That's why it gets broken, whether it can be in this direction or in this direction. But it will be breaking at 45 degree, and these are called shear lips. And as you can see, it is not something it will be very easily gone. Like in brittle, in brittle failure, you'll be seeing the surface as a very shiny, and it will not be having any. Here you can see some fibrous and then shear bands, shear lips and all you'll be able to see. But in when brittle fracture will be happening, the surface will be shiny. Shiny, and then in ductile fracture, the surface, as soon as you see the surface, you'll be having small fibrous at the top, and that is like how the cup and cone will happen. So yeah, now you guys can ask me the questions. The spinal shear fracture at 45 angle related to the tensile direction. That is called pure shear failure will be happening at the end. Yeah. Now anyone has doubt in this section?
Actually, as go on,
yes.
Please.
We'll proceed further.
Yeah, we will proceed further. But then two people were asking something else. Like,
actually, regarding the relationship with the stress concentration in making and fracture of tensile specimen.
So that's how it is done. So the answer was correct. The C was correct. Statement 1 is not true, but statement 2 is true. Like necking will happen in the middle of the sample. No, it is not true. It can happen anywhere. But necking happens especially when internal flaws in the material are mostly concentrated. So now next question.
Yeah, sorry for interrupting. I just had one small doubt in question number 2, just an extension.
Yes. Yes.
You're discussing about this fracture toughness and toughness, right? I recall from last, I think, the week 2's class that sir had mentioned that in fracture mechanics, one finds recommendations separately for handling thin structures, which is under plane stress and
plane strain.
Yeah, sorry. Thin structures
plane
under
stress
plane
and plane strain.
and thick structures under plane strain. And sir mentions fracture toughness is greater for thin specimens, which is under plane stress, than thick structures.
Yes.
Can you just throw some light on that? Because I think it's related to this particular question.
Yes. No, I don't think so. It is related to this question. The fracture toughness, yeah, like, yeah, if you try to find out the fracture toughness of the material, okay, with the thickness, if you change the thickness of the sample, initially it will be increasing the fracture toughness and then it reduces. In this region, it will be plane strain condition. And in this will be plane stress condition. Yeah, here the thickness of the material, normal X and Y, as sir said, like it will be similar only. Consider in mode 1, we will just consider mode 1. It is kind of easy. Some crack is present and we are applying load. And the thickness of the material is not much. It is very less. And the similar one, and the thickness of the material is very high. This is the thickness. So here what actually happens is like if as the thickness of the material is very low, the principal stresses that acting in X3 will be less actually. I've just give me 1 minute. Written something about it somewhere. Yeah. Yeah, one of the principal stresses, that is correct, only what I was studying. One of the principal stresses will be 0. So here we can consider only in X many. Sigma 1 and sigma 2 will be acting major, like if the thickness of the material is more. So sigma 3 will be not acting, like one of the principal stresses consider this sigma 3 is 0. So then it's kind of better it's if it is principal stresses, that is higher stresses acting in the material, one among them get reduced means like I'm trying to put it in a layman term, like but in detail I have to also see a little bit more. But this is how it is, like one of the principal stresses will be 0. If one of the principal stresses is 0 means that like the severity of the material will be less, so like it will be acting in plane, so stresses will be uniformly, I mean, it will be acting only in XY, and then how much ever the load we applied, it will be in only in XY, and then 1 and 2 principal stresses are only will be present here. Principal stress 1, 2, 3, all three will be present, and then you have to take care of all three. That's the reason. That's all. So yeah, toughness of the material initially increases with increasing the thickness of the plate, but then it saturates, it reaches highest, and then it reduces with increasing further thickness. That's why the fracture toughness is very much required for us. Like fracture, if higher the fracture toughness, the better the property. I mean, fractured, it avoids the crack for the group propagation. So yeah, like we want higher fracture toughness, so we have to see where is the maximum fracture toughness you get, and then it's better if you use in plane stress condition only rather than plane strain condition, because the fracture toughness reduces in plane strain condition.
Okay.
Did it?
Yeah. I just understood in this. So I think maybe you said when sigma 3 is to 0, if we apply the same that von Mises yield criteria, we will get something which is larger than the yield stress. I mean, if that sigma 1 minus sigma 2 whole square plus, because you said
Yes,
sigma
yes,
3
yes,
becomes,
yes,
yeah.
yes, correct.
Yeah. So then if all these differences of these principal stresses is greater than the 2 yield, that is 2 sigma square
How
ys,
much?
then the material will not yield. So I think that may be the reason, I suppose.
Yes, yes, correct. If one of the principal stresses is reduced, yes, correct. Yeah, thanks for correlating these two.
Okay.
Madam, you are comparing this toughness with fracture toughness, but toughness is not a function of your thickness, no?
This is a fracture toughness which we are talking.
Correct. But toughness is nothing to do with the thickness.
No, toughness. See, we are in the stress strain curve. We are taking, we are dividing the area, right? Stress per, like we are applying load per unit area. So here, like it's taken care. Like with increasing, with varying the area or with varying the thickness, like you are here you are normalizing it. So yeah, with varying thickness, the toughness of the material will not vary, but it is not true completely. Also, some amount of toughness variation will be there, depends on thickness of the material. Ideally, it shouldn't, but it will.
Okay.
So for now, we will just talk about fracture toughness. If you want, I can check on that also, like whether it will increase or not. Like,
It's okay.
okay. So yeah, thanks for reminding this point. Who asked this, Suresh or who? Yeah. So yeah. Fourth question, ceramics are used to build vanes in gas turbine due to their ability to work in high temperature. Which of the approach or criteria in fracture mechanics can be used to study them under high temperature? LEFM, EPFM, leak before break, either A or B. So it's a straightforward answer.
EPFM.
And whoever answers this, I want the reason behind that also.
For according to the lectures, what Sir has mentioned, there is a transition temperature for everything. Ceramic is actually a metal material. Whenever the temperature is above the transition temperature, or else at high temperature, we normally prefer to use EPFM.
Correct. That's correct. Who was this?
Naveen.
Huh?
Naveen.
Naveen, Naveen, the one who joined first.
And can
That's
you
right. Yeah, yes, correct, correct, Naveen. So EPFM is the right answer. Anyone has any doubt? No, right? Like it's clear, right? It's a straightforward answer. So yeah, who will give this answer? Identify the mode of loading in the case of pressure vessel subjected to internal pressure. Mode 1, mode 2, mode 3, mixed mode.
It is mode 1.
This is also, yes, sir has discussed this point also in the lecture. I think so. It's lecture 5 or something, lecture 5 or 6. Yeah, it's a mode 1. Like anyone has doubt in this?
Madam, not with respect to this question, but no, there is a similar question in the assignment.
Yeah,
I saw. In a tube, the internal, due to internal pressure, what is the if there is a crack at an angle?
What will be if the crack is at an angle?
They are just not able to.
And the question is like there is a crack at an angle.
Yes. And how is the loading applied?
At what angle, whether this loading will be subjected to mode 1 or mode 2 or mode 3, or is a combined mode or is a mixed mode, like that. They are asking whether what angle this is subjected to mode 1, or else at what angle it is subjected to mode 2. Question is in that way.
So what is the criteria for mode 1 and mode 2, mode 3? You tell me, you guys tell me.
Mode 1 is like an opening of a crack.
Yes. Displacement of the crack should be perpendicular. To the electric axis. Yes. So if it is at that particular angle and you wanted the stresses to be acting in perpendicular to that one, so you try to rotate the stresses present or try to rotate the plane in such a way that getting the point?
There is one doubt regarding the crack nomenclature or like that.
Regarding, can you come again?
Ma'am, in a crack, which is the leading edge? Whether can you tell me which is the leading edge or else? In some cases, there is a displacement perpendicular to the leading edge of the crack.
So this is the way the crack is propagating, right, in this direction.
Yes, ma'am.
So even the loads are applying in this direction, and then it is getting directed in. But then the surface, the crack surface which is forming is perpendicular to that one.
Oh, okay.
We will discuss that question next week.
Okay.
Like I got the question which you guys are asking. Like even I saw the questions. Even I'm solving it actually.
Okay. Okay.
So we will solve that question in the next.
If not direct the question, just please answer me this. Actually, in internal tube, should we consider that both ends are closed?
Internal tubes.
That
both
is the tube. Hello.
Yeah. You guys are not able to hear me? Hello.
We can hear you.
Yeah, Suresh, right? Yeah, Suresh.
No, this tube to be considered as the ends are closed.
It's a tube. Ends will be closed, right?
Ends will be closed. Okay. Then in the crack, which is a perpendicular direction, that is also subjected to mode 1 loading.
Yes, it is still subjected to mode 1 loading because crack is propagating in this direction and the crack surface is happening at 90 degrees, and the load which is happening, we are not applying any load in this direction. Only in one direction the loads are happening, right? Or we are not applying load in this way. You got the point?
Yes, madam.
Yeah.
Madam, just to none of the case, I feel, I don't know, none of the case, there will
Actually,
be a mode 3 loading.
None of the
No.
classes is mode 3 loading.
Yeah,
Newspaper tearing, sir gave example, right?
Pardon?
Newspaper tearing is a mode 3, right? Even
No.
tearing.
In the tube, in a pressurized tube, whatever may be the angle, there will not be any mode 3 loading. But all the loading will be either
in
mode 2
mode 1
or mode 1.
or mixed mode.
Yeah, mixed mode. There
Yeah,
will not be any
that
mode
is
3.
right.
Okay. No, whether the way of our understanding is correct or not, just want to
So
check.
there is, okay, let me clarify this point. Like, I don't think so there will be mode 3, like, we will be having this type of, no, I don't think so we'll be having this type of stresses applied in pressure vessel. No,
Yes.
there will be no mode 3. No.
Okay, madam,
No,
please.
there will be no mode 3. So it is in mode 1. The answer is mode 1. So stress corrosion cracking, yeah, I have one case study also for this. We can do it later. And I discussed a little bit last class also, stress corrosion cracking, how it starts and how it propagates and all. So stress corrosion cracking is induced due to the effect of applied stress on the material, due to the combined effect of constant applied stress and corrosive environment, due to the effect of compressive stresses on the material, applied stress, compressive stress, due to the combined effect of alternating stress and corrosive environment. So what is the right answer?
D.
Huh?
D.
Who said it?
Naveen.
Naveen. Okay, so I'm really calling out the names now. AJ is who then?
I am AJ.
Yeah, your full name?
Alfred.
Alfred. So next question you're answering, by the way, okay? So yeah, due to combined effect of constant applied stress as well as the corrosive environment.
It can be alternating stress also, right? Just had a doubt. Arjun here.
Usually, stress corrosion cracking can be happening because of alternating stresses like fatigue. That will be called fatigue plus corrosion. This when alternating stresses will be happening, that will be called fatigue. Now there is no fatigue. It's just stress corrosion cracking. That's all.
This Aloha incident that said Boeing aircraft, it had corrosion and also it was under the pressurization cycle. Is it an example of corrosion?
So yeah, I understand what you're telling. Like it's not like every time will be just in tension, it will be happening. Most of the material, of course, it will undergo fatigue. It's not every time we'll be putting in pressure. So yeah, even chances are there. Even in fatigue also, corrosion will happen. And then the case study which I'm trying to discuss, right? That is actually the sample was under fatigue, as well as the corrosion happened, and then stress corrosion. Because of stress corrosion, the crack initiated and then it propagated and then broke. Yeah, that will also happen. Yes. And that you can identify using the after doing the analysis of the how the cracks are growing, how the cracks are oriented. From that you can tell whether it is just because of normal tensile or compressive load, or because of fatigue, or because of alternating stresses. You'll be able to see beach marks, and if you go higher magnification, striations and all, you'll be able to see. I'll be showing you that in one of the case study.
Thank you.
So fine, we will discuss now only. Anyway, I feel like this is kind of important. So So actually, this is one of the problem in MRPL. Cooling tower in MRPL, the cooling towers, as you know, most of the places, any industries, they usually have cooling tower. So here it will be, the center will be the gearbox, like it will be where the motor and all will be fixed, and then there will be fan, complete fan arm. This the one which connects the motor as well as the what is this blade. Between that there will be a fan arm. Consider thinking your fan. In between there is a motor, and then there is a blades, like, and in between there is a small the thing which connects the fan arm type, which connects both motor as well as the blade, right? That similar type of structure is present even in the cooling tower fan arms. I'll show you the actual image. This is just graphical image, schematic image. This will be the where the motor and all will be fixed, and this will be the blade, and between these two connecting is fan arm. Whichever will be connecting between these two is called fan arm. The problem is that whenever this fan arm gets broken, um, there were some problems with only on the fan arm. The fan arm was made up of mild steel, and then it was, as you can see, this line and all, right? This is a top wave, and you can see few things coming out of it, and these things were welded. The samples were welded to this circular one. I'll just show you the actual image so that you'll be able to. This is how the actual things will be present. This is fan arm. This is a motor, and there you'll be having a blades. These like blades will be present. And then between two fan arms, you'll be having a stiffener so that it will be standing properly. As you can see, these things are present. To hold the stiffeners, you have added few more things, hinges or something. So these will be welded. So this sample, these were welded, and to fix here, there is also one more that was also welded. So you'll be having something like this. Here there will be one, as you can see here, the welding happened here. Here one welding they have done, and here one welding they have done. And this one also they connected using welding, and this is also weld sample. So and we try to do, this is how the fan arm was present. This is a mild steel. You can think that when mild steel is like it is getting affected, only what will happen, you can just replace it. It doesn't cost much for us, like it's just a milestone, just do the casting and then do the welding, and then you can just keep it. But the problem was the failure was happening many, not just one fan arm was happening, failure of the one fan arm was happening, many fan arms were happening continuously. So as you can see here, there is something called carbon fiber shaft. So here it is present carbon fiber shaft. Even though when the failure of the fan arm happened, this blade used to go and hit the carbon fiber shaft. And the carbon fiber shaft is kind of very costly, and then like you cannot you cannot even afford to replace it. Like it's kind of costly. So basically, and then once the fan arm is broken, even the productivity gets reduced. Not only just you're losing the money, in order to replace it, you have to not only just replace the fan arm, you have to replace even the shaft also. Like once it gets broken, it's not like it will break and then the whole cooling tower, you guys have seen cooling towers, it will be very big cooling towers. Like it's very big actually. So this will go on, it will not like it will stop then only. It will keep on rotating like till it becomes, it goes hit another blade or something like that. Even the blade gets destroyed, the shaft gets destroyed, kind of whole cooling tower construction gets destroyed. So it until then, not now the money is lost, the time is lost. You have to replace just because of one mild steel component, you have to replace literally whole cooling tower, like that whole shaft and blades and everything, because it will be damaging blades as well, because it surrounding is made up of concrete. So once it goes, yes. Please keep it muted. So that was a problem that MRPL was suffering, and for the analysis showed that when the most of the cracks were present near the stress concentration region only, when SolidWorks, when the whole component were drawn using SolidWorks and then saw where the stress concentration regions are present, it was present near the weld region as well as near the edges where it is like, you can see it's around 90 degrees present. And you can see the cracks, how the cracks were present. So, and along with that, the condition where the material was, the whole MRPL was present was in Mangalore. As you guys know, Mangalore is a coastal region. MRPL, Mangalore Premier, limited, some petroleum limited, Mangalore, MRPL. Yeah, refinery. Yeah, refinery one. So Mangalore has high chloride concentration in the atmosphere because sea is very near. Along with that, it's an industry. It will be having many pollutants. So the in the air itself, you will be having a lot of corrosive environment. Like, so that's starting a pitting, especially on the mild steel. It is not that difficult. The reason why it happened mainly on mild steel, not on any other components, because the blade was made up of polymer. Even the carbon fibers were made up of polymer. So not much severity was present. But here, this is a very small component. Like, as you can see, the motor is fine, the blade is fine. Only the small component which connects the blade and the motor is the one which is giving us so much trouble. So, and then they saw that because of the corrosive environment present in the atmosphere, started pitting on the surface and then started a started forming a corrosive layer on the sample. As you can see, that lot of corrosion is happening here also, you can see. And then the pits started forming. These pits will be having some amount of crack tip. And then, as you know, this one, the whole sample is in it will be keep on rotating. It's a fan arm, right? So it will be having varying in stresses. The stresses will be varying in the material fan arm. And then finally, what happened because of the corrosive environment along with the stresses present, stress corrosion cracking started happening. And when you saw the microstructure of the material, you could see one of the microstructure. There was a corrosion pit where the fracture started originating, and because of the varying stresses, the fatigue beach marks were able to observe. And then once it reached the enough crack length, it failed failed in a brittle manner, and you can see the failure in brittle manner in brittle river bed pattern. And when further seen in the corrosion, the pits were observed like this. And along with that, when stress analysis were done, the stress concentration was present more in this hinges, more near the corners. And then even where fan arm goes and sits in the motor and where it holds the blade, because of the weight of the blade, they calculate the weight of each blade and then they put that much amount, and then they saw and they were able to see that the stresses were higher in this region as well. And one of the example to show that crack was present in that region as well. And then because of the welding and weld joint, the stresses were present as it was also weld joint at 90 degrees. The stress concentration was also higher in that region, and you can see the one crack corresponding to that. And similarly, the another crack corresponding to this. So in order to avoid this, once the welding was done, you have to do the proper heat treatment. And then, like, once the heat treatment was given properly, avoid keeping it 90 degrees so that the stress concentration region will not be high. We have to change the design of the fan arm. We cannot just neglect, it's a small component in the whole cooling tower, what it can do. Like, we cannot neglect even the small parts. We have to keep in mind each and everything. And so we have to take care of this as well. And then if possible, even coat the material so that the stress corrosion cracking stress at least gets avoided. And then design the whole component in such a way the stresses gets uniformly distributed, not just stress concentration regions will be high in any particular region. If it was just one failure, they can say it is fine, but then many failures occurred in very short period of time. That's why this became very crucial, and then was immediately attention was required to rectify the errors. So this is one of the case study. As you can see, I hope you guys enjoyed this case study.
Adding a few more points to that case study.
Yes.
And the analysis with what tool was that performed?
If I'm not wrong, it was in SolidWorks. It was way too long back. I did not do it by the way.
And I understand like this design should be pretty old design, right?
Yeah, I think so. This was how the design that industry had. We took the similar design and then we tried to rectify it by doing the analysis. That's all. What was the problem, where it was originated? This we did not do the design.
Yeah, and one more mistake was that see your earlier one of your simulation picture clearly told that stress concentration was high at one of the edges. And before welding, like, and at that particular point welding was done, that I would say that's a blunder. So when stress when stress concentration is high at a particular region, and if weld is done on that, despite whatever heat treatment, post weld heat treatment we do in service condition, it really mess up.
That's a valid point.
And one more, this material, because why I told it's a old design, the components that are exposed to chlorofluorides and particularly the corrosive environment, that should never be in mild steel. Because, and the designs that were made like 2-3 decades back, there were like no awareness and like wanted to spend. And now it has been most of the materials that were exposed to this environment were like replaced with duplex 2205 and those kind of materials. And not at least, like, if they couldn't spend, like, they at least go for austenitic grade stainless steels.
Austenitic, oh yeah. Usually even in houses in Mangalore region, they use austenitic stainless steel, yes.
And in my opinion, I would say that the question what we were discussing, like what I have learned apart from my experience, I won't say that it is because of like applied loads or like alternating loads. I would say both would contribute. So
both
in
applied and okay.
Stress concentration, like it's a combined effect of applied mechanical loads and the corrosive environment. That's my opinion.
Applied mechanical loads and then corrosive. Yes.
Yeah, and I have seen like failures in corrosive environment in both like what you say, the static loads as well as in alternating loads. I have come across. So I would say like the answer should be combination of B and D.
Oh, for this one?
Yeah.
B and D. No, see, if it was combined alternating stresses, then we don't call it stress corrosion cracking. We call fatigue, I guess. Like if I'm not wrong, Sarah has discussed about that point. That's the reason why I'm telling that stress corrosion cracking is not correct for alternating stress. That's called along with the fatigue. We have to get the word fatigue here. The terminology is not correct. Here it's just stress is happening. That's all. Only stress, not alternating stress or anything.
Stress. When we say stress,
that part, when we say stress, like what makes a difference? Like let it be whatever kind of stress. Tensile
stress or compressive stress.
Tensile or compression. It will not be alternating. It will not be going in tensile and compression. It will not be going in tensile and compression. It will not be alternating. It will be just one type of stress.
And for D, I think it will be fatigue corrosion. There is a corrosion
called
fatigue corrosion.
Yeah, exactly. Fatigue corrosion. That is the word I was searching for. Fatigue corrosion. So I understand what you're trying to say, but then this is stress corrosion cracking, right? So only one type of stresses will be applied, not alternating stress. Okay. This is called fatigue corrosion.
I can give an example. Normally, stress corrosion cracking is seen.
No, can you come again?
Normally, stress corrosion cracking is observed in pressure vessels.
Yeah, because it will be always in one type of loading, and then it's not like something that will be load unload will be doing. Yes, correct. And then along with the pressure we'll be having a hydrogen embrittlement also, because like steam and all will be present. So hydrogen embrittlement is one of the mechanisms Sir will be discussing in the third week, right? That's one. So so is it fine now? Like the answer right now, this is alternating stress is called fatigue corrosion, not stress corrosion cracking.
Yes, madam. It looks to be
Yes.
correct. Thank you. Thanks to Mr. Alfred also. Just he has nicely added.
Yes.
Can we go to that other next question?
Yes. Using fracture mechanics, we can get the information regarding the safety of life and the safe life of the component, fracture toughness of the material, stress intensity factor of cracks, critical flaw size. So who will be answering this? AJ, right?
Safe
I
life
said
A.
age. Huh?
Safe life A.
Okay, safe life. We'll be able to
Critical
get
flaw size.
size.
Critical flaw size.
Okay.
think
So who
altogether
said
will
this?
come, I
Who
think
is
so.
telling this?
Suresh.
Suresh. This is AJ. Okay.
B also, ma'am.
Huh? Who is telling this?
B also.
Who told this?
Kannan.
Huh? Amay.
Kannan.
Kamal.
Kannan.
Colonel. Okay. K or C? I'm keeping K. Okay. Actually, the answer is all. Even Sir told in one of the lecture that once we complete the fracture mechanics, we should be able to find out the life of the component. What is the critical flaw size that can be allowed so that the fracture will not happen, and then the load, how much we are applying, can be safely applied, and the stress intensity factor near the crack region, and the fracture toughness of the material. All these things we should be able to answer. Along with that, we should be able to answer when we apply some load, when search showed that it crack propagated in different region. That is because like different region was happening because the velocity that was at which that crack was it was beyond relax um, velocity. So that's why we got the crack in all different 3 different regions. It was propagating in 4 different regions actually. So we should be able to answer all those things. So once the fracture mechanics is done, we should be able to answer all those things in the similar way. So using fracture mechanics, we get the information, all of it. Fracture toughness of the material also will be able to understand using fracture mechanics once the whole lectures are done. So all are right in this. Anyone has objection in this? So we'll go to the next point. So LEFM can be applied for
Polymers below glass transition temperature.
polymer below glass transition temperature. That's it. What is LEFM, by the way?
Linear elastic fracture mechanics.
So it will be applied for which type of materials?
For high strength, normal high strength materials.
High strength materials, correct, which will be having less ductile, less plastic deformation. So is ceramic a high strength material?
B and D.
What? Can you come again?
B and D. B and D.
B and D. So what did ceramic composites do to you?
Ceramics brittle material. So
Yes.
brittle material means LEFM, that comes under LEFM category. And then polymers below.
Where does the ceramic composite goes? So where does mild steel go, by the way?
And still ductile material, right?
Yes, mild steel ductile material. So which type, what can be applied for mild steel? What study can be applied?
Elastoplastic mechanism.
Yes. So for ceramic, what we can apply?
Brittle material, LEFM, linear elastic fracture mechanics.
Okay. Fine. This for this one. What about for ceramic composites? That is also correct.
Composites, ceramic composites, I'm not sure. It is
also LEFM.
Yes.
Because that is also high strength material.
Yes. So like we are trying to increase the strength, or we'll be trying to make the ceramic composites. The main problem in ceramics is it will be having a lot of porosities. And then once porosities also acts as a stress concentration region. We do know that. It's not just a crack. It is difficult to make a complete compact ceramic material. So in ceramic composites, what we do, we add a reinforcements or like some matrix and reinforcements in such a way that cracks propagation gets stopped. Like crack will anyway propagate, we cannot do anything. But then in order to avoid that propagation, like we add either steel, small steel rods, or it can be in fibrous way, or it can be longitudinal fibers, so that crack gets arrested near this boundary, the composite or metal boundary, or composite or polymer boundary, between any boundary. So that's how the composites are formed, so that the fault that material that ceramic has can be overcome by making a composites. So we can add metal or polymer to the ceramics in order to enhance the property that ceramic has. The strength of
But
the
what,
ceramic is, yes.
yeah, madam, what about if the ceramic composites at high temperature? Then in that case
So when
also,
ceramic is temperature is very high temperature, like it will be acting like a ductile material, not like a brittle. That's the reason why ceramic, previously I said EPFM for ceramic. When we use a ceramic, for instance, you consider metal, when you go below nil ductile temperature, that is like very low temperature. For steel, for instance, you consider like it is in, you put it in liquid nitrogen and do the testing in tensile, it will break as a brittle. And but then if you take it a little bit higher temperature, like how the hot rolling is done, they do take it to a little bit higher temperature and then they do the hot rolling, so that the deformation will be easier, and the it will be very ductile, and then like you can make it as thin as possible. But at the same time, when you do it at room temperature, you cannot reduce the thickness of the material very high, because the slip system and all those things will not go there for now. In the similar way, when this ceramic in room temperature, like it acts like a brittle material, but when you take it to higher temperature, that is very high temperature, then it behaves like a ductile material. Got the point?
yes, ma'am.
So that's why we use at high temperature for ceramics EPFM. So these are the right answers. So coming to next question, time available for inspection of crack in a material can be determined from crack growth curve with the help of first, who will be answering this? At the same time, I want you, those people to answer what is a crack growth curve also. So who will be answering this?
Permissible crack length.
Cycles.
Number of cycles?
Yes,
Who is telling number of cycles?
Naveen.
Naveen, okay. Naveen is telling number of cycles.
Permissible crack length, I'll go for.
Suresh, is it Suresh?
Arjun.
Arjun, okay. Arjun is telling permissible crack length. Is it correct? Both are correct?
Both
Huh?
A and D, sorry.
What is crack length? Someone is telling crack length safety factor. Who told crack length safety factor?
No. Permissible crack length I was telling.
Ajay, you told permissible crack length. Okay, and does minimum crack length has nothing to do with it? How much time it is required?
Minimum crack length, I think it's not concerned for us.
It is
Madam,
not
minimum crack length is the length of the crack which can be detectable using any NDT method. Is it like that?
Yes, it is something that we can detect using NDT method, or like you can, yeah, that is a minimum crack length. But that much amount of crack is present for sure. It means that like that that is the length of the crack that is present in your material. So the initial length of your crack in the material doesn't say anything regarding how much time it is available for inspection of the crack.
No, it is not, sir. It doesn't deal with
It is not?
This is not the, no, this minimum crack length is not the correct answer for the given question.
But the right answer is it depends upon how much is a permissible, how much up to what length the crack can be allowed to grow, and what is the minimum, how much was the initial crack length of the material, and how many cycles we applied, like whether we applied 10,000, 10 power 6 cycles or like any cycles. It can be alternating cycles, by the way. Alternating stresses will be applied. So any number of cycles that we, how many number of cycles we applied until now, all these things will come to a picture. Because if the initial minimum crack length that was present in the material was very small, and then to take to go to permissible crack length for a given stress applied, for any stress applied, it might take more time. For if the stress is low, it will take more time to go to permissible crack length. If it is very high stress applied, then it will take in very less time, it will go to in very less number of cycles, it will go to permissible crack length. But if the crack size initially itself was very high, what if the crack was initially itself was like the permissible crack length, then even without applying any number of cycles, you will be having failure, right? Sure, right? That is a true fact. You cannot tell a minimum crack length doesn't play any role in for inspection, how much time it is available for inspection of the crack, right? But initially, you have to do the inspection. How much? That's the reason why in every industry, especially aircraft industry or military industry, any component is done. Once any component is done, they do NDT, non-destructive testing. They do ultrasonic or X-ray or radiography or anything for that matter. So they will find out how much is how much is a crack length that is present. Is it well below the allowed crack length? And it should be obviously below permissible crack length. That is for sure. But then it should be also in permissible crack length should be attained during the service life, not in the initially only you'll be having permissible crack length and then you'll put it to the servicing load. No, like first initially you should have way lower than the allowed crack length, that is permissible crack length. Is it like explained fine? The answer is these three actually.
Yeah, it's correct, madam. It looks correct.
It looks correct.
Just
Fine.
Yeah, fine. Actually, the crack length safety factor. What is it? Can you explain?
Even I don't know, like I have to see that crack length safety factor, like up to like this is the one crack length safety factor is the NC, right? Like how that is like a safety factor, like which we use, that how much permissible critical crack length by. This is the formula.
Ratio of critical length by permissible crack length.
Yeah, ratio of critical length by permissible crack length. So that is already covered in, yeah, permissible crack length is dependent on this NC factor. So I don't think so it's required, like it is required or not. We can increase the factors. Let me check with this point then.
You
like,
mean to say it is like a factor of
it
safety?
is already, yeah, it is a factor of safety anyway, and it is kind of already included in API. I don't know whether we have to consider this or not. And especially when the graph was done, you remember, like this was something like this. This is a crack size. This was time taken to attain that crack. And this was a minimum that NDT can identify your minimum crack length. And then consider this is a permissible one. And then you have this much time left now. And this is a permissible. We are allowing this much. And then fracture is happening I mean, critical crack length is somewhere here. This is a critical crack length. So this is at time 0. This is at time 1. This is at time 2. This is critical. You see, so the time that we'll be having is this period of time, right? In this period of time, we will have to do the inspection, right?
Yes.
So here the things that required is AP, A minimum, and then how many number of cycles that we applied and how much time it was required. This is, so we get this, we get the crack length based on the number of cycles that we applied. Before that we had how the crack length is going to vary with increasing the cycle. Before that we had a graph for that also. So I don't think so crack length safety factor will be required. So only 3 factors. Fine.
Yes, ma'am. Thank you.
So the question 10, which of these?
Small question. Before
Yes.
before your timelines, just in the present assignment, just we have a doubt. Actually, there was a notation in one of the question. There is a load, there was a bending moment, and there is one more notation. Is it for that T? It is indicated as T. Is it the twisting moment or torsion? In one of the questions, it was asked.
It was in live assignment.
Actually, in the live assignment.
Yeah, in the live assignment, in one of the questions, the
Okay.
mode, which mode 1, mode 2, mode 3, it was asked like that.
Can I clarify you at the end? Is
Yeah,
it fine?
sure. Yeah, so
We will open and then I'll see and then I'll try to clarify what the.
sure.
Which of these is or true regarding crack length safety factor that we just now saw the crack length safety factor is AC by AP, right? So someone please tell me quickly so that we can go to the next question. It detects the length of the crack should be lower than the permissible crack length. It is equal to the design safety factor. It is a ratio of critical crack length to the permissible crack length. It can be used to determine the time for inspection. Come on, we will solve it soon and then we'll go. Next question.
See you only.
Yeah, and C.
Correct. Yes. It detects the length of the crack should be allowed, should be lower than the, it tells that how much should be the allowed crack length in the material for particular apply load. That's answer. Choose the correct group. Choose the correct group. This we have. You remember, like we have parameter. Like we used to have energy release, and then that was based on energy based, and it was used for LEFM. So similar this B and D.
Yes.
CTOD, that is crack tip opening displacement, was based on displacement mode, correct? And it was used for EPFM, correct? And you told stress intensity factor, right? Stress intensity factor was based on stress, correct? And it was used for LEFM, correct? So C is wrong. J integral, it was based on energy. That was energy based.
Maybe A is also correct. Maybe, I don't know.
Yes, A is also correct. Yes, A is also correct because energy release rate, like that G which was there, the one which they gave in in the honor of Griffith, was based on energy based and it was used for LEFM.
J integral, that why how C is wrong? Option C. J integral also comes under EPFM.
Yeah, is it based on which one?
Energy based.
Acha, it is energy based. Okay.
Okay.
Yes.
Choose the correct statement related to cup and cone. See, I've explained really well. I really want the answer properly now.
AC and D.
It occurs.
AC and D.
C and D.
Thankfully. Yeah. Finally. Perfect. So correctly identify the mode of failures in this one. And then you also have to tell me which mode is what. So this is which mode, by the way?
Third mode.
That is mixed
Huh?
mode.
Third
Mode.
Mode 3.
Mode 3.
Mode 3.
Tearing.
This is
Mode 1.
Opening.
mode
Yes.
1. We don't have time. Okay, fine. So we know the factors, how it will be varying also, right? How the stresses are applied and how the crack grows. It is not in plane. These two will be in plane. That is the reason why the stress intensity, toughness, fracture toughness will be easier to find out for mode 1 and mode 2 compared to that of mode 3, because the stress applied and as well as the crack that will be propagating will be not in the same plane. Yeah, we came to the last few questions left. With the reference to the crack growth curve, answer the following questions. So, what is the time available for inspection? I told you guys how much is the time that is available. We cannot allow the crack to go beyond permissible limit. We have to be well below this, and this is the minimum crack length that will be present in our material. So this is the window that we have in order to inspect. Like for this is for fixed or load, or like sorry for this will be for varying load only. For how much amount of varying load or like what type of load, that will be kind of fixed. So when that is fixed, this is the in this interval in this interval we should be able to do the inspection, so that we will be getting the will not be allowing the crack to grow beyond permissible, and then failure will not happen. Before that only we can see that crack is about to approach permissible limit, and we can change the component. So can everyone solve the problem, this problem? How much is the time available for inspection?
4.5.
3.9.
They're asking 10 per minute, 10 per 6, sorry, 10 per 6 cycles.
3.9 into 10 per 6.
3.9 into 10 per
6.
And do I have any other answers?
Yes, ma'am. It is not 3.9. Actually, 4,500 minus 6.
And whether it's 4.5 into 10 power 8.
10 power 5 only.
At
One
the
by
second
one, I'll
time
take all the
interval.
answers. This is 4.5, right?
4.5
This is
into power.
450 minus
10 power
this is
8.
10 power 5, so 0.6.
Okay.
Because it's 10 power 5 and this is 10 power 8. So sir wants in 10 power 6. So I convert everything into 10 power 6. And this is the value we get. Tell me how much you are getting.
449.4 into 10 to the power of 6.
440?
9.6.
It's 449.4.
449.4 into 10 to the power of 6.
Let me see the answer. Yeah. With the reference, it's the same question. What is a crack length safety factor? From this figure only, try to depict what and all is required to calculate crack length safety factor, and try to get it and then give me the answer. And tell me what is the answer.
Crack length safety factor, it is coming very high, madam. That 2222.
Can you tell me how you did?
2000. 10 to the power of 12 divided by 4.5 into 10 to the power of 8.
10 power 12 divided by?
4.5 into 10 to the power of 8.
Can you tell me why you did this?
Actually, we take length only.
2.5.
2.14.
How much ever is the critical length that we cannot allow?
Oh, okay.
Divided by how much it is allowed.
Oh, sorry.
Yes. How much is the answer?
2.5.
Let me see. His answer. I'll give you the answer. No, the answer is 2.14.
Yes.
Can someone cross verify? Just do the 15 divided by 7.
Yeah, correct. It's 2.14.
It's 2.14. Yes. I forgot to. It is there. It came 2.1. So the last question: if the crack length safety factor is taken as 3.75, sorry, what would be the value of permissible crack length? If you're taking NC as 3.75, what will be AP?
Four.
Who gave the answer 4? Anyone else has any other answer? 4 is the right answer. Yeah, we completed today's lecture exactly at 8. Yeah, now
Whether
I'll
these
be
lectures
sharing.
will be uploaded or
Yes, it will be uploaded, but last time what happened, last time what happened, actually, we discussed the live session, which was already there, like live assignments, and I was not supposed to do that. So that's why I did not upload still. I'll be uploading tomorrow. I'll be uploading both the today's as well as last week's. I'll be uploading. I'll be sharing to everyone also. And I'll be sharing the case study that we did. If you guys are interested, you can go through that paper. And one doubt we had was like, yeah, I'll stop the recording for now.